Well, nonlinear means not lines. In fact, think about chapter 2. We've done two kinds of nonlinear functions. We've done the polynomials, which this even includes our quadratics, which look like parabolas, and we've done rationals. So when I say nonlinear inequality, I really mean polynomial inequality, rational inequality. That's what we're going to do in chapter 2. So we're going to rely on the yellow sheets and the blue sheets for some characteristics of those polynomials and rationals. Of course, inequalities, you guys know, less than or equal to, greater than or equal to. I assume you know and can read the difference. I will just put them up here on the board so that if you know that has always been a struggle for you to read them correctly, you can write them down. Okay. I always try to make it so like my variable would be on the left, the left side, and my number that I want to be greater than or equal to or whatever would be on the right side. That way I can read it. And then the less thans always look like L's. Okay, so that's helpful for me. Okay, now you don't need to draw these graphs into your notebook. We're just, on this slide, going to try to make sense of what's going to happen with polynomial inequalities, because these all look like polynomials to me. Probably A and C are quadratics, and B looks like to me opposite end behavior, 2 terms, 3 zeros, probably a cubic. There's nothing weird at the zeros where it bends to make me think it has odd multiplicities more than 1. Okay, so, you know, like sometimes we give you pictures of graphs and then we like name the graph. So I'm going to name each of these. I'm going to call A, I'll call f of x. For this cubic polynomial, I'll go ahead and call it g of x. And then I'll call C h of x so they each have a new name, okay, or a different name. And when we're talking about polynomial inequalities, what are we talking about? I'm going to be asking you questions like this. So like, you're not going to have the graph. You're just going to have the function f of x is an equation. And I'm going to be asking questions like, when is f of x greater than or equal to 0? So if you're looking at graph A, which is f of x, and you're looking for the places on the graph, if you were seeing it visually, where f of x was greater than or equal to 0, another way to say that is to say y is greater than or equal to 0. Where are you looking on the graph? Aiden says above the x-axis. Aren't all those points above the x-axis places where your y value is greater than 0? It's in the positive range. Okay, I like that. So we're kind of focused on this section here. Notice 2 points that would be really important to us are going to be these x-intercepts. So it looks like -3 and 1. What's true about the function at the x-intercepts? What's the value of the function at -3? 0. Its y value is 0. And same for 1, right? If you're on the x-axis, if you are an x-intercept, then your y value is 0. So should those be included in my inequality? F of x is greater than or equal to 0? Yeah. So your answers today are going to look like things like this. -3 to -1 inclusive using brackets on them. Okay. Now, maybe I'll give you some polynomial that has a little bit more happening. So I could ask in like g of x, when is g of x less than 0? So before, Aiden told us to look above the x-axis. If we're looking for less than 0, now we're looking below the x-axis. And depending on the shape of your graph, like notice you have 2 sections that sit below the x-axis. So our job today, we're going to be doing it algebraically, not graphically. But we're going to be trying to find where are the sections where it is negative. Now, again, the x-intercepts are really important points. Would you include them this time? G of x is less than 0? No, we wouldn't want to include these x-intercepts. So I'm going to mark them as open circles because those are the places where g of x equals 0. So then sometimes for the zeros, instead of using brackets, we would use parentheses. So we would say g of x is less than 0 from negative infinity to, looks like, negative 3. That takes care of this end behavior that's falling on the left. And then in union with 0 to 2, it looks like. So you can have like multiple intervals where you're above 0 or below 0. And you'll have to ask yourself, should I include the x-intercept or not? It would depend. Do you have or equals to? Okay, now C is just kind of an interesting one to kind of give you some perspective here. You know, if I asked in C for h of x, when is h of x greater than 0? You say never, nowhere, not applicable, none, null set, you know, just something to say that doesn't happen. If I change that to say when is h of x greater than or equal to 0, do you have an answer now? Yeah, where does that happen? At the vertex, that must have even multiplicity. It's churning at the x-axis. So the only place where it's equal to 0 is at 3. I just want to do this one so I can model for you. If you want to say 3 in interval notation, you just put 3 in brackets. You don't need to say 3 comma 3. That's kind of redundant. So if you just have a single answer, you just put it in brackets. And then I could ask other questions like, when is h of x less than or equal to 0? Always, negative infinity to infinity, all real numbers. If I wanted to say when is h of x less than 0? Negative infinity to 3 in union with 3 to infinity. Skip 3, right? So your job today is to be figuring out where these intervals are without a graph. Okay. Notice in all of the graphs and in my intervals, what are the important numbers? The x-intercepts. So that's the big takeaway from that visual, is we're looking at x-intercepts. So I would jot these steps down in your notebook. Today can be one of those days in math where everything makes sense in the room. It is super easy lesson. I'm good. I'm golden. And then I get home and I have no idea what I'm doing. It isn't hard. It's just like you have to know what and why you're doing it. So this will be helpful. Before you start any of my nonlinear inequalities, please make sure one side is equal to 0. If it's not equal to 0, you'll move things around so that it is. Okay. The second step is find your critical values. Now, this is what the book calls them. They're the places on your graph where you can change from positive to negative or negative to positive. And we just identified the places where that's possible is all on the x-axis, right? When y equals 0, if I cross the x-axis, then change my sign. So for polynomials, we can say that happens at x-intercepts, or we might say zeros. Okay, and I'm going to put a qualifier on there, the real zeros. If you had imaginary zeros, you wouldn't really worry about it. Now, below that, I say leave a line, because we're going to do rationals after we do a polynomial example. So, like, what are the critical values? Are they the same, or are they different for a rational function? And then here's step 3. Step 3 says, test an x value in each interval to test if f of x is positive or negative. Hey, Mr. Wills.
What?
That's exciting. Mr. Wills. This is the part where people get tired or they get confused. So this is the part you really want to focus on today when we're doing our examples. I try not to get too bogged down in the calculation of the f of x, the y value. I don't really care if f of 3 is 42. I just care that f of 3 is positive. So I'll show you some like tips for how you can do that and like eliminate some of the calculating, and that'll make it easier. And then it's good measure to just like check every interval. A lot of times they alternate, but you can have negative areas next to other negative areas, like we saw with the even multiplicity graph C. Okay. So we'll test those areas. Okay, now leave 2 blanks because I'm gonna give you some warnings for rational functions once we do the rational functions. And then step 4 is to write out your answer. So now you've done all this work to test the intervals, but now you have to answer, like we did from the graph, where those intervals are. So if I gave you a graph, you could all do this. You would look for when it's above or below the x-axis. I'm just going to give you the function equation, and we're going to try to pull out the parts that we need and test the intervals without making a graph. Because we know, like from our worksheets, graphing is a lot of work. We're going to have to do all that and then do inequalities. Make sure your answers are in interval notation, brackets are included, parentheses are excluded, and then I'll show you the number line graph answer. It's like super easy. The book uses brackets and parentheses, so that's what I say to use. I wouldn't necessarily take off if you used open and close circles, but I just do it the way the book does. Okay, let's do an example. Oh, I went too far. X cubed minus 3x squared minus x greater than negative 3. Okay, step 1, make sure one side of the inequality is equal to 0. Since that's not true, what could we do? Add 3 to the other side. I'm just going to take a side note here so that like I remember at the end what I'm actually trying to do. Greater than 0. In the end, I'm going to be looking for sections of my graph that are positives, right? Those would be the sections that are greater than 0, where f of x is positive. Okay, so my f of x is this cubic polynomial right here. And we said that the critical values, the places where the graph could change its sign, would happen at the x-axis and be the x-intercepts. So you now have to find the critical values by finding the zeros of the polynomial. This is nice. In this section, the polynomials will always factor. Okay, so I'm not going to give you one. We have to do rational zero test, Descartes' rule sign, synthetic guess and check, and then at the end still go through all the work of testing intervals, right? So if you want to make a little note to yourself, all your polynomials are going to factor. So this one has 4 terms. We're going to have to factor by grouping. Take out an x squared from the first 2 terms. From the last 2 terms, they don't really share anything in common, but you should know from factor by grouping, like if there's a negative x, you always want to take out the negative. So I'm going to bring out a negative 1 from both terms, which that changes both of these to their opposites, so it's going to be x minus 3. And of course, you know they're going to factor, so these 2 groups of parentheses should be the same, right? If your polynomial is not factoring, it's you, not me. I wouldn't give you one that didn't factor. It factors, so you can figure it out. And then you could find your critical values here. Some of us might notice that this is difference of perfect squares. I'm going to write it in completely factored form because it will be easier for my checks, as you'll see momentarily. So x squared minus 1 is really x plus 1, x minus 1. which means my critical values are what values? 1, -1, and 3. So those are the x-intercepts on my polynomial, right? If I were going to graph it. Okay, so here's like step 2 where we start checking it. I'm going to make a number line. I'm going to put these numbers on it in the order from least to greatest. -1, 1, and 3. And by making this number line, you now have a visual for how many intervals you need to check. In this polynomial, because it potentially crosses the graph 3 times, there's 4 intervals that I need to figure out if I'm positive or negative. Now there's 2 ways for you to figure that out. You can take x's and you can plug them into the polynomial function f of x equals this cubic polynomial. But then you actually have to do like calculations. You have to figure out what x cubed is, and that can be a lot if we don't have a calculator, right? So this line down here that's completely factored, it's the same function just in factored form. I'm going to check some values in my factored form. So I go to my number line and I usually just move from left to right. I got to pick something that's left of -1. Of course I can choose -2 or -3. When I'm on the ends, I kind of like to exaggerate my number just because a number further out makes it really clear what sign it's going to be. So I might say, let me check f of -10. Like, what if I put -10 in for x? What kind of answer will I get out for y? Okay. So in the factored form, all I'm looking at is -10 minus 3 would be negative. -10 plus 1 would be negative. And -10 minus 1 would be negative. I mean, that's pretty clear, right? All 3 factors are negatives. So this is negative times negative times negative. Do I even care what the numbers are? No, I just know my answer is going to be negative. 3 negatives make it negative. All the points in that area have to be negative. Now let me try this area between -1 and 1. So obviously I'm going to check 0. Now I could plug 0 into these 3 factors. 0, though, I'm actually going to plug into that original function because that's just the y-intercept, and the y-intercept is the constant, which is 3, and that's positive. So by the y-intercept, I know this section is positive. We okay with that? These are all zeros. 3 is my answer. It's positive. Okay, check probably 2. I don't want to use this one up at the top because I have to do 2 cubed is 8, minus 12, minus 2. Then I actually have to calculate the numbers. Down here I can just say 2 minus 3 is negative. 2 plus 1 is positive. 2 minus 1 is positive. So this is a negative times a positive, which is a negative. Now you can decide, like when you're doing your homework, like I can really do that negative times positive in my head. I'm writing it down, of course, because it's notes, right? So like some of this you might be able to do in your head, but I will caution you on quizzes and tests. Show me your checks, otherwise I have no idea how you got your answer. So it's helpful to me if you show me your work. Last one, I got to pick something greater than 3, so I'll pick something bigger like 10 again. And what I like about picking that big number, x equals 10, when I plug it in over here, it's obviously positive, positive, positive. It doesn't take me to do much math to know all 3 things are positive. So that's also a positive. Okay, so now all you've done is checked the intervals for what signs they are. You still have to answer the question of when the function is greater than 0. Well, we decided at the very beginning that greater than 0 meant we were looking for positive sections, so we see them now. It's between -1 and 1. And it's beyond 3, so 3 to infinity. I know infinities have parentheses. Do I want to include the x-intercepts? Why not? It's greater than 0, but not greater than or equal to 0. And at all of these points, f of -1 is equal to 0. F of 1 is equal to 0. F of 3 is equal to 0. So these are all equal to zeros. They are your x-intercepts. So we don't want to include them. We do parentheses for all. That's how we say our answer. We didn't even need the graph for that. Now the second part of your answer is that number line. I usually make a new one just because my other one gets really crowded with stuff as I mark my notes. So I'm going to do parenthesis, parenthesis, shade in between, parenthesis, shade beyond. That's all we want. You could also do open, open, open. It's the same thing. But the book does it with parentheses and brackets. Okay, questions, concerns about what I did? And now I do just want to say one thing before I leave this one. Back up to my checks. This is a good way for you to get started to check things. But some of us are also really good with that visual graph stuff. So if I looked at this polynomial function over here, this cubic one, the leading coefficient is positive, so the right side rises. The degree is odd, so the left side falls. Which if you think about that, that would have to mean that on the right side of this graph, I have to be positive after that 0, because I'm just going to be going up towards positive infinity. So it must be positive after 3. And if the left side is falling, it must be negative after -1, or before -1, because that whole graph is just going down, down, down to negative infinity. Then you can use things like multiplicity. So if you recognize that all 3 of your critical points had odd multiplicities of 1, that would have meant that you would have crossed the axis at those zeros. So when you know you had negative in the first section, when you cross the 0, it would have went to positive. Cross the 0, it would have went to negative. Cross the 0, it would be positive. So it also makes sense if you like to think about the graph visually. I will warn you, if you use that method, to be on the lookout for even multiplicities. Because even multiplicities mean you could have a negative next to a negative. It'll turn at the 0, or a positive next to a positive. Okay, last thing really quickly, we got to do rationals. Bear with me here. I'm going to highlight this graph A. This is a rational function, right? I'm going to highlight this graph. I'm going to draw the positive, when y is positive, so when it's above the x-axis, I'm going to draw it in blue. And when it's below the x-axis, I'm going to draw it in red. So it's above the x-axis right here. And then I'm switching, and I'm going below the x-axis. Okay, so I just changed from positive to negative. What's a critical point right there? -1. It represents an x-intercept. So a rational function can change its sign at x-intercepts or zeros, just like polynomials. And then I had this negative section, and now when I go to graph the rest of the polynomial, the rest of the rational is all positive. It's all above that horizontal asymptote of y equals 1. So what's the critical value in between the red and the blue? 2, which represents a vertical asymptote. So we need to make one adjustment to what our critical values are for rational functions, you can change signs at x-intercepts. You can also change signs at vertical asymptotes. Do you have to? No, but you could. Okay. So let's add that into number 2. Rational is x-intercepts and vertical asymptotes. From 2,6, I know the x-intercept is set n of x, my numerator equal to 0, and my vertical asymptote is set d of x equal to 0, the denominator. So just to kind of refresh our memory, like how will we find the x-intercepts, how will we find the vertical asymptotes? Set our numerators and denominators equal to 0. Now, if you notice that there was a hole, if you would account for the hole, that doesn't necessarily mean that you change signs. Okay, and then here's my warnings in 3. So make sure you get your warnings on your notes. Star, circle, highlight, something. Okay, you have to pay attention to, like on that polynomial one, we just knew all those critical values we were equal to 0. So we like didn't include them because we were just greater than, and we didn't want 0. But you'll have to pay attention when you have x-intercepts and vertical asymptotes. You can sometimes include the x-intercept if it has or equals 0. But never should you ever include the vertical asymptote because it's undefined. There is no function value there, so there's never a graph. Okay, so the vertical asymptote always has parentheses. The x-intercept depends on the inequality sign. Okay, we'll do our example for rationals. We're going to do 3x minus 5 over x minus 3 less than or equal to 1. Of course, we want one side of the inequality to equal 0, so we're going to subtract 1. So 3x minus 5 over x minus 3 minus 1 is less than or equal to 0. Now there's a slight problem here. When I taught you rational functions in section 2.6, they were always n of x over d of x, and there was never anything added on the back. So in order for us to use our rules, like set the numerator equal to 0, set the denominator equal to 0, we need to combine these. We need to actually subtract them. Do you agree this is subtracting 1 over 1? And in order to subtract fractions, you need common denominators. So you're using your skill from Algebra 2 of adding and subtracting rational functions. So if you had to move a number over, you're going to have to multiply it top and bottom by the denominator. So that now I have a denominator of x minus 3. And up in the numerator, I just have to combine like terms. Be real careful on this one because it was minus 1. I want to subtract the x. And I also want to subtract the negative 3. So that's really negative x plus 3, which would be 2x minus 2. So that's just like being very detail-oriented right there. We never did rational functions with a plus or minus behind them. So our old rules wouldn't apply until we got it as a numerator over a denominator. Okay. You could think in your head, factor out a 2 right here. It's 2 times x minus 1, but there is no hole that I have to worry about. So I can go ahead and do my critical values. That's going to be an x-intercept. Set my numerator equal to 0. So x equals 1. And that's going to be a vertical asymptote. Set my denominator equal to 0. So that's an x equals 3. So this time I only have 2 critical values, which will split my sections up into 3. So I only have to check 3 intervals. 1 and 3. I'm going to go ahead and mark this right now. F of 1 is 0. F of 3 is undefined, right? That's my vertical asymptote. I'll never include 3, but maybe I'll include 0. It depends. It depends on my inequality. Since it says less than or equal to 0, I'm looking for sections that are negative or 0. Okay, so I'm looking for negative and I'm looking for 0. So it looks like I will be including 1, but I won't be including 3. Okay, do some checks. Let's see, I'm going to check f of 0. 0 is always pretty easy to plug in. With a rational function, it's easiest if you have your numerator and your denominator factored. You know, check for your whole, and then just plug into the numerator and denominator factors. So I only have 1. The numerator, if I put in 0, is going to be negative, and the denominator is going to be negative. So a negative over a negative is a positive. So this section is positive. And then I'll check 2. If I put 2 in, 2 times 2 minus 2, that's positive. 2 minus 3 is negative. So a positive over a negative is a negative. And you might guess that the last one's going to be positive. I would always caution you to check it, right? It doesn't take long to check. Pick something greater than 3. Maybe I'll do 10. Then the numerator is positive and the denominator is positive. That took me 2 seconds, but I have confirmed it is indeed positive. Are we okay with where I'm plugging in for my check? I'm plugging my check in to the numerator and the denominator right over here. Okay. So we're looking for negatives and zeros, which means we want that middle section. And we said we would include 1, but we will never include 3 because it's a vertical asymptote. So my solution would be 1, 3, bracket, parenthesis. And then I could draw that graph, 1, 3, bracket, parenthesis, shade. Okay, questions, concerns? Your chapter 2 test on Thursday is going to be no calculator. So you will have inequalities on that test, but you won't be able to calculate, well, I mean, you could calculate, take the time to calculate each individual part. But I would really focus on using this like factored form and check your factors, are they positive or negatives, to determine your signs. So I practiced that in my notes. Let's see.